Hello ladies and gentlemen, I am Dr. Claudia Albers, Planet X researcher and professional physicist. And today I'd like to talk to you about another one of my articles. This one is entitled The Electrical Nature of Earthquakes. Now, an 8.2 magnitude earthquake struck Mexico on September 8, 2017. And green and blue lights were seen in the sky. This is a photograph from Mexico, where we can see this bluish light in the sky. So these lights were observed at the same time as the earthquake, and they appear to be associated with the earthquake. Now, some people believe that these lights are not actually connected to earthquakes, but they are due to failing power stations that may occur during earthquakes. But the phenomenon has been occurring since before the use of electricity, so it does seem to be associated with earthquakes. Then the fact that light is emitted from the air in the region above the earthquake zone would suggest that the air is ionized above that region, and air becomes ionized when there is an electrical potential across it. Just like the gas in a discharge tube becomes ionized when a potential difference is applied across the electrodes. So here we see a discharge tube. It has electrodes. One will be the anode, the other one the cathode. A high voltage is applied across the electrodes, and that ionizes the gas in the tube. And ionization means that the atoms lose electrons, and these are usually the outer energy level electrons. And these electrons then flow and produce a current, whilst the ions, the positive ions that are left, flow in the opposite direction. So this in total produces a current across the electrodes. Then some of the electrons are captured and the atoms go back to the ground state, and when that happens, a photon is emitted, and we detect these photons as light if they are in the visible light range. So in the case of the light produced over Mexico, there would be blue light photons emitted from the gas in the atmosphere. And this is similar to what happens during aurora, which occurs when there are geomagnetic storms. And these also result due to ionization of atmospheric atoms and molecules. And this happens because they are impacted by high energy particles from the solar wind, and also because of impact by electromagnetic radiation, which occurs when there are solar flares. So the fact that lights are observed during earthquakes suggests that earthquakes are electrical in nature. This, of course, would not be surprising, as there is now overwhelming evidence that we live in an electrical universe, and therefore the Earth must be a charged object and capable of having electrical discharges. Now, the Earth's upper atmosphere becomes ionized due to incoming ionized particles in the solar wind, as I have mentioned, and due to the impact of solar flares. And we do know that there was a strong X 9.3 class solar flare on September 6, 2017, and that soon after that 2 CMEs impacted the Earth's magnetosphere, and this would result in very strong ionization of the Earth's ionosphere. And in fact, the resulting impacts led to a G4 geomagnetic storm and extremely bright aurorae in Northern Europe. And this possibly is associated to this earthquake. So let's look further at what these electrical effects can produce. First of all, we know that on Earth we have lightning, and lightning is a result of electrical breakdown between a point at a high electrical potential and one at a low electrical potential. And it is the same as the spark that occurs between two electrodes when a high potential difference is applied across them. So what we see here is lightning coming from the atmosphere and impacting the surface of the Earth. This means that there is a breakdown. So there was a high potential difference across, and this lightning discharge equalizes the potential. So in other words, it brings the charge from high up in the atmosphere and takes it down into the surface of the Earth. And the same thing happens when we have a high potential difference across electrodes. We get these electrical discharges, which also break down, which equalize the potential. Now, the high ionization of the Earth's ionosphere would create a potential difference between the upper atmosphere and the surface of the Earth, and also anywhere inside the Earth. This would lead to ionization of air molecules and induce currents in the atmosphere, leading to lightning between the atmosphere and the surface. But if the rocks inside the Earth can also be ionized, just like the air, then we would expect currents inside the Earth as well, and possibly electrical breakdown. In other words, a type of lightning happening inside the surface of the Earth. Now, the surface of the Earth is usually taken to be neutral, but it is constantly being hit by lightning, so it must have a reserve of charge and must therefore have stored electrical potential energy. And Dr. Friedman Freund from San Jose State University wrote in a 2003 paper that the lights that have been associated with earthquakes for millennia suggest that earthquakes are electrical in nature. He also enumerated other phenomena usually associated with strong earthquakes, namely bulging of the Earth's surface, changing water levels in water wells, ground-hugging fog, lights from ridges and mountain tops, low-frequency electromagnetic emission, strange animal behavior, magnetic field anomalies, temperature anomalies of up to several degrees and detected by satellites. And he suggested that these can be attributed to the electrical nature of earthquakes. And he explained this nature as being associated with the fact that rocky material under pressure becomes semiconducting. Now, a semiconductor is somewhere between an insulator and a conductor. It doesn't have natural free electrons, but when an electric potential is applied, electrons leave an atom and can move in a certain direction. And when they leave the atom, and of course all the atoms are in a crystal structure because this is a solid state material, and they leave behind what's called a hole, and the hole is able to move in the opposite direction to the electrons. And this leads to conduction, much like what you see in an ionized gas. So here we see the black dots are the electrons. They are able to leave an atom and move in a free manner, or almost a free manner, not quite like in metals, but somewhat free. But it leaves behind what's called a hole. And these electrons then hop from atom to atom, as we see here. It hops from there to there. And in the meantime, the holes that are left behind are filled and emptied so that it looks like they move in the opposite direction. So this would cause a current, so a negative electric current in this way in the direction of the electrons, and a positive electric current in the opposite direction. And so large currents can therefore be produced in this way inside rocks, inside the Earth. And these large currents can produce heat and expansion of rocks. And we can then get electromagnetic emission at different frequencies. So that would be photons being given off of different frequencies. We would get magnetic anomalies because the moment we have a current, we have an electric field, and a moving electric field leads to magnetic fields. And so these changing electric fields would produce these magnetic anomalies. And this may, of course, go unnoticed most of the time, but when the ionosphere is charged way beyond normal, such as what we had after the X9 solar flare, we may have effects where this semiconductor produced field is not strong enough. And in that case, we may have a breakdown in the circuit inside the Earth. And in other words, this would result in a lightning type discharge, which occurs in the interior of the Earth, which would lead to acoustic or seismic waves, which are analogous to the thunder phenomena associated to lightning discharges. So in the Earth's atmosphere, whenever there is lightning, we see the light, that the photons that come from the ionization of air molecules. And soon after we see the lightning, we hear thunder. And thunder or sound waves due to the vibration of air molecules when the air is superheated by the lightning discharge. So these sound waves are basically the same as acoustic waves, which inside the Earth are called seismic waves. So these are actually thunder. So in this case, it's probable that the charge stored deep within the Earth becomes involved, and this leads to the production of an earthquake emerging from the point where the discharge occurred. And this is illustrated in this figure. So here we see an illustration of the Earth. This would be the Earth's surface. This would be the core of the Earth. And because of a very high electric potential difference, possibly between the ionosphere and the center of the Earth, we would get a discharge. And this would produce currents at different levels. So we'd possibly have some kind of current flowing through there. And this point would then become like an electrode. And then we would then get a discharge, which would be like a lightning discharge between the core of the Earth and that point. So this purple line indicates a lightning type discharge. And we would then possibly get multiple earthquakes with different epicenters. We have this larger one would indicate a larger magnitude earthquake. And then we would have a seismic wave, which is the same as subterranean thunder, coming from the point where the electric discharge ended. And this point would be the earthquake epicenter or the lightning strike point. And this is therefore how the electrical theory would explain the production of earthquakes. And as you can see, it originates with the ionosphere, and even that, it's before that, what actually occurs is something happens on the sun, and it causes the Earth's atmosphere to be ionized, for our ionosphere to be highly charged. And in the end, it is that. So in other words, it starts with the sun that leads to an earthquake. And this is possibly the reason that often every time we have a geomagnetic storm, every time our magnetosphere is impacted by something that happened on the sun, we see an increase in earthquakes. And the presence of the stellar cores in the sun's corona, close to the sun, are destabilizing the sun, making it more active, and in turn making earthquakes stronger and more numerous inside the earth. So, but I also want to mention one thing, that it's important to realize that even though conduction inside a solid lattice structure, which would be what we have as rocks inside the earth, can be explained in terms of semiconductor p-hole theory, that in practice particles are not solid objects. They are actually energy confined by fields. And fields will change the configuration of this confined energy. So in the end, we are actually dealing with energy and fields whenever we have matter and current interacting. And so in conclusion, earthquakes, just like everything else in the universe, seem to be electrical in nature. An earthquake seems to actually be due to lightning inside the solid or rocky material beneath the surface of the earth. And an earthquake seismic wave is due to the resulting subterranean thunder moving away from the lightning strike point, which is then also an earthquake epicenter. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.